Yeah, so today we're going to talk about the ray optics module. Ray optics module where the light is treated as particles, as a rays. Okay, so here we will try to model very simple case where we launch the rays of 1 watt, light source of 1 watt. And for example, we launch 5 rays and each of them is considered as 0.2 watt because total is around 1 watt. So zero point 0.2 into 5 number of rays, which will be around totaling around 1 watt. We can again create the medium. So this is the medium that we are working with, and that medium could be in any it could be a lossy material, it could be a it could be a lossless material, whatever medium that we want it could be. Okay, we can also model these optical fibers that I've drawn here. So uh, you can see a total in reflection that is going to happen, and then you can also see what is the transmittance. You can see because of the bend that it is making, um, what is the losses because of the bend. So is there any uh, in any photon actually comes out because of this bending? Those things could also be modeled. Okay, so a quick raise of hands of how many people would be doing the hands-on along with me. Okay, that's good. I had also shared one let me share that again. Self-assessment form. It's a self-assessment form. So
Hi, Vikram. Can I ask a question?
yeah, please go
Yeah.
ahead.
Yeah. So regarding the self-assessment form, is it possible? It's just a request. Is it possible to? You mentioned a deadline. Is it possible to increase the
Yeah, the
deadline?
deadline is today 8 p.m.
Yeah, but I'm asking to
Extend.
increase it. Yeah. Yeah. Is it possible?
Yeah. So we can have it. I mean, so by when do you want to complete it? So it's a
Yeah.
self-assessment. Okay, so it's like I mean, yeah, I mean, it's up to you. Yes, you can complete it anytime that you want, just for you to understand like whether you want to self-assess to understand that whether you understood your course or not. If there are some, these are some kind of simple questions which will help you to uh, just self-assess. Yeah.
Okay. I would like
So
to.
there's
Yeah.
no
I would like.
deadline. So that doesn't matter. Deadline doesn't matter. That's what I'm saying.
Okay. Okay. Okay.
Excuse me,
Okay.
sir. Will you be providing a participation certificate for this?
Yeah. E-certificate will be sharing you by the next week.
Okay.
Yeah, at the registered email ID. It will be shared.
Okay. Thank you.
Okay. Yeah. Okay. Looks good. So where was I? So yeah. So you need to go to File, Application, New. Okay. Sorry. File, New, Model Wizard. Okay, and then choose the space dimension as 3D. This is what we have been doing till now. No change. Only the change will now come as optics, and then we go to ray optics. And we, instead of the electromagnetic wave frequency domain, we use geometric optics now. And click on add. I'll wait for a few moments for you guys to add this geometric optics.
So sorry, I missed. It's 3D or 2D?
3D.
Okay.
So now you can see that dependent variables are like so many, 6 dependent variables. So each ray, okay, that you're launching, that each ray that you're launching, this is a very important part. Each ray that you're launching, it has 6 dependent variable. So you can just assume that so 3 of them are for the position. This is qx, qy, qz are for the position. So this is qx, qy, qz, that is its coordinate. Okay, and it has, this is a vector. Okay, and then it has three wave vector components, means the direction of that. Okay, so kx, ky, kz. mentions the direction, associated direction. So each ray has 6 ones. So now assume that you want to model around 1000. If you want to model around 1000 uh, rays, okay, so you need to just multiply it by 6. So it's actually 6000 DOF. Okay, so directly with the rays. Now there would be some degree of freedom from coming from the geometry as well. The good part with geometric optics is that if there is a big domain, you don't need to mesh the domain. The rays do not need a domain to propagate. Like what you see in ray optics, you actually wave optics, you have seen it needs a domain to propagate, right? Air domain needs to be there, but here you do not need to. You just need to model only the interfaces. For example, we are going to model going to model one kind of a plane wave, which is one kind of a surface which is going to launch the rays, and then we're going to model a lens which is going to focus this light source. Okay, simple thing
Then,
that we'll model. Yeah.
my name is Faraz. I have a question that you mentioned the degree of freedom of why you multiplied it with 6,000.
Yeah, so 6, you can see this is the 3 and this is
Okay.
the 3. So each ray has tied up with 6 dependent variable. It will be solving at a single instant of time.
Okay, and it will always be like this, like always it will be
Yes.
six or
Yeah,
can.
you see over here, right? So while you are
Okay,
adding this geometric optics showing dependent variables as 6. So it always be 6, at least 6.
okay,
Means if there is something new dependent variable that you want to tie up with something, then it's something different. But at least this 6 would always be there.
thank you.
Okay. Okay, that's good. So I hope you have added geometric optics. Then you go to study, and then we go for ray tracing. Okay, ray tracing study. Just click on done. So now you can see that it is completed geometry. So completely is blank now. So now we are going to work in dimensions of mm. So you can go to geometry and change it to mm because that's better, right? So usually the lens and all those things that we work with is in order of mm's. So maybe it's a lens of diameter 25 mm, trying to focus at 25 mm, focal length of 25 mm perhaps. Okay. Okay. So let us now make this light source. Okay, there are different ways of making the light source. One is the imaginary surface, but I want to do something like which is visually present, because that is more simple. So what I do, I just right click on the geometry, I click on. So I hope you guys are with me, and just quick raise of hands just to know if you guys are with me. Okay, looks good. Okay, cool. So just right click on the geometry and click on work plane. Okay, if you click on work plane, okay, so I want to launch something in x direction. Okay, so I can make my work plane in yz plane. So I might change my plane from xy to yz. Okay, so this is something what I'm trying to create a boundary in my 3D geometry. Okay, in a 3D geometry I'm trying to make one boundary. Okay, so I create a work plane, and from this work plane, once I go inside the work plane, I'll just wait for a few moments for you guys to create a work plane. This work plane I'm given, this plane is YZ plane. Okay, just make sure that it is YZ plane. Okay, then you go to plane geometry, right click on plane geometry and create one small circle. Because your lens you're assuming to be of around 25 mm, you can make this circle of 10 mm, so 20 mm light source. and just click on build all, you will see that. Okay, the radius is 10 mm. Okay, so I hope you have created this circle of 10 mm diameter radius. Just click on form union and click on build all, so you can actually see where that particular. Just click on this go to 3D view, go to view, default view, and you can see, zoom out just to see like it is there or not. Okay, so this is the light source that you have created. Okay, I will wait for a few moments for you guys to make complete this.
Sir, can you go to the circle one? I just miss it.
Yeah, circle one is just 10 mm diameter radius at the center. You can keep it at center.
Yeah, 10 mm. Okay.
Yeah. Okay. Okay. Looks good. Phew. Next, what we need to do is we need to add one lens in front. Okay. So the good part of COMSOL is that there is facility to directly add the geometry of the lens from the part library. So just right click on the geometry one. You can go to the parts and you can go to part library. Just right click on geometry, parts, and then part library. Okay. Then you can go to ray optics, 3D, which kind of lens that you want to model. So there are a lot of options like spherical lens, cylindrical lens. So I can just use a doublet, triplet lens. Or any of the legacy of the lens, concave, convex, concave, plano convex. Okay, so all of them you can actually use. For example, I will use equiconvex. Okay, so you can go to the ray optics legacy, spherical lens, and equiconvex lens 3D. Then click on add to geometry. Okay, wait for a few moments for you guys to search this.
So could you explain how you came to this part libraries again?
Yeah, just right click on the geometry, go to the parts, and this is the part library. Okay, then you go to ray optics, legacy, spherical lens. Okay. So I hope you are able to add this to geometry. Add to geometry. Then it will ask you what you want to add. So the best way would be to specify effective focal length. Okay. So you know what is the focal length. That's in our hands. Okay. So here you can see the focal length I can actually change with whatever I want. So right now it's 10 centimeter. Diameter is around 25 mm. This is the focal length. So if you want, you can also change the focal length whatever you want. Which will actually just click on build all. You will see, get to know where is that lens, convex lens. So actually it's over here. It's overlapping. So you cannot see. So you just move it in the right hand side. Displacement around 10. Yeah. Okay. You can also change the focal length if you want, but I'm not changing it as of now. Just shift it towards the right hand side even further. Okay. So anyone facing any problem or any challenge to make this geometry?
Sir, the spherical equiconvex lens 3D legacy. After that, we need to click the add to geometry, right?
Yeah, correct. And then
But
change
there
the
is
geometry whatever you want from here, but I'm not changing anything.
okay, but there is some message like select part variant.
Sorry.
There is coming some
In that
message.
choose that focal length.
Focal length. Okay.
Okay. Okay. I hope you are able to create this.
This is Jayakrishan.
Yeah.
Sir, I have a doubt. I am having four options actually for the lenses.
Okay.
Like what have you selected actually?
So where are you getting four options? Like once you click on add to geometry,
Yeah, like four options.
means
Specify
is
radius of
it
curve.
spherical convex lens material
Yes,
geometry?
convex
3D
lens
legacy.
3D.
Yeah, you choose that effective focal length out of that four option.
No, I have two focal length: effective focal length and center thickness, effective focal length and edge thickness.
Which thickness?
Edge thickness.
Edge thickness. I can use center thickness. Not a problem. Yeah.
Okay. Yes, sir, but the values are entirely different.
You're not getting these values.
Yes.
You're not getting these values.
No. My default focal length is 125,
Okay.
and
And what is the
D diameter is 50 millimeter.
50? Okay.
Yes, and the TC is 10 millimeter.
So this example were using which version of COMSOL?
6.2.
This is the same one that I have sent to you.
No, sir, which is 6.2, 3.1. I don't know exactly.
Okay.
Let me check it.
But that's fine. Don't worry. So but you're able to see something. Nah? Main thing is that you can change it. If whatever is that 50, right, you can change it to 25. Focal length is 200. 25, you can change to 100. TC also you can change it. So It
Okay.
doesn't matter. Okay. So important part that you are able to import a convex lens.
Yes, and I'm also having refractive index.
Refractive index over here as
Yeah,
well.
okay, okay, yeah, got it, got it. Yeah.
Yeah. And this is the incident ray direction, means it's actually propagating in x direction. So that's what it mentions. Okay. That's good. So I hope you are able to add this geometry. A quick raise of hands of how many people are able to add this, or if you're facing any problems. Okay, looks good. Jakrishna, you have a question?
No, sir, no, no.
You can
I'm,
mute yourself then. Yeah, so noise will be coming. Okay, looks good. So now so let us go to the next part now. The next part is to apply a material property for this one. Okay, just right click on the material and add material from library. Okay, and then you can go to built-in, and then you can go to silica glass. Just double click on this and you will see that this material would be assigned to this domain. Okay. So I will wait for a few moments for you guys to add silica glass.
Hello, sir.
Yeah.
Actually, you have added the lens, the convex lens. Is there any axis you have changed? Actually, in my case, the circle and the spherical lens are not the same plane.
Okay.
Axis of
So yeah.
axis
Work
types.
plane in part is XY. You can make it XY, something like this one. Is it the same? You can just check it. Is it like this one?
ZW axis, yeah. Same.
Or if you want to, the rotate option is also there, so you can rotate it. For example, like this one. If it's not changing, you just play around with this axis of rotation and then rotate it. Important part, the center should actually match.
Okay, sir.
Okay. Are you able to do it?
Let me try.
Okay. Let me know others. Otherwise, you can share your screen. I can just look into it.
Okay.
Okay.
And circle, sir, that is center, right?
Yeah. Everything is center.
Center. Okay, sir, I'm sharing. Just look into.
Okay. Yeah.
Sorry, sir. Actually, my system is hanging. I think.
Okay. No problem.
Yeah.
You can see this recording. No problem. If once it starts, just let me know.
Okay, okay.
Okay. No problem. Okay. So I hope others have been able to create this lens. Okay. And add this silica glass material to this lens. Next thing is to launch the ray from here. So just right click on the geometric optics. Okay. And you can use this release from boundary option. Right click on geometric optics and click on release from boundary. Once you add the release from boundary, select this particular boundary. Okay.
This option is not available in my version.
Which version are you using?
5.3.
This release from something, release from inlet, something would be there. Actually, can you share your screen? I will just look into it. Boundary release something, boundary release something should be there. Can you share your screen? Yeah, just right click on geometric optics. Oh, I cannot see actually the after you do the right click on this, I cannot see.
Sir,
Perhaps you can
it
you
is
have to
release from grid, release from data file. There is option of only release accumulator, ray detector, material discontinuity,
yeah.
wall, mirror, grating,
So
inlet,
what you can do,
illuminated
you can you share by sharing again the screen instead of sharing the console, sharing the console.
Hmm.
Can you once you share right, you just
Okay.
click on entire screen
Okay.
rather than the window, any particular window. Share the entire screen. Yeah. Now inlet. Yeah, this is inlet is the option.
Inlet.
Okay. Yeah, inlet.
Yes, sir.
The same thing as what we are doing now. Okay.
Okay, sir.
Okay, looks good. So let me just share my screen again. So once you inlet was the old boundary condition, now it is released from boundary. Okay, so this is the release from boundary. How many number of rays that you want to launch? I just want to launch uh, five, maybe 10 number of rays. Okay, and how you want to launch? You want to launch using a projection plane grid or mesh based or density based. Density based means you can have more number of rays in the center, and then as you come out, it would be lower number of rays. Okay, some kind of density profile you can have. Okay, but to start with, I will just use a simple plane grid. So it will have an associated with the 10 number of rays with it inside. So it will kind of grid create it and then it will launch the rays. In which direction I want to launch? I want to launch in X direction. So I can write it as X 100. Okay. So it will launch around X direction. Okay. You can also launch perpendicular or normal direction to this boundary using this enabling this one. So if you enable this, then you will see T1, T2. There's two tangential direction, that is actually Y and Z, and then one is normal, that is the perpendicular to this boundary. Okay.
Sir, how the tenders are distributed? Can we have control over it?
Yeah, yeah. So you can either use a mesh. I will just come to that. As a starting, I'm just putting this projection plane grid. In some time, I will show you how you can control that using intensity. This is equidistance. This guy is like equidistance kind of uniform plane wave
Sir,
propagation. Yeah.
I have a question.
Mm-hmm.
Like if we check the specified tangential and normal vector components box,
Hmm.
it is showing on arrow in an outward direction, right? Is it the ray
Yeah,
of
yeah.
propagation of
Yeah,
light?
ray propagate direction. Yeah, yeah. So if you want to do an opposite, then just write minus over here. Then
Okay.
it will be
Okay.
opposite.
Okay.
Yeah. Okay. And you can also launch the rays whether it be conical. For example, in the case of a laser, you can use a conical light source with a particular half angle, okay, hemispherical or Lambertian. So accordingly, you can change it. So as of now, I'm keeping just 100. If you click on conical, you can see that you can again tell how many rays in the number of rays in vector space, wave vector space, how much would be there. So what is the cone angle, what is the direction of cone that you are releasing, right? So all these things are there, but right now I'm just putting it as expression as 100. Okay. Mesh, just go to the mesh and click on build all. You will see that the mesh is only done for the boundaries and this domain. The air domain which is inside is used by this refractive index. For example, now you want to model something in the water. Okay, so you can change this refractive index in the geometrical optics physics. Okay. Also, right now the light source is monochromatic. You can also make it this polychromatic. I will come to that in some time. How to launch a polychromatic light source. Right now, it's a perfectly deterministic monochromatic light source. Okay. Okay. So, quick raise of hands. Like, how many people are along with me, or anyone is facing a problem till now?
Sir, also later on, can you once focus on what parameters do we need to tune for a source which can imitate very close to a laser kind of an application?
Sorry, can you come again?
What I'm saying is, sir, maybe later on, can you
So
tell us
this will
certain?
conical would be the most relevant to the laser source.
Okay.
Okay, yeah, conical with what is the half angle you can mention over here. Okay, and kind of density that you want to have. Okay, so all these are in your hands.
Sir, how we will be able to define the other properties of the light source?
Such as
Coherence, or if it is a light.
coherence is cannot be modeled with ray optics thing. So for coherence and other properties like interference and all those things, you have to model the complete wave optics part. Okay, interference is very difficult to do it with the ray optics. It's next to impossible to do it with the ray optics. Okay, so if you are looking for
So,
this,
the characteristics of the light source is not really important in here.
sorry,
The characteristics of the light source
yeah. So what is the question? Characteristics of light source.
cannot be defined. I mean, the
So that's what means. For example, if you are you want to know the instrumentation part. You want to see a lens of lenses or lens of optical components. How it is changing the light source. Okay, direction of light source, focusing, and all those things. You're trying to show the image which is forming. Okay, so all those things you want to model, then you can use this ray optics modeling.
so
But you
basic,
want, sorry.
basically ABCD metrics and Jones metrics and all.
Yeah, yeah. Eventually, those things also you can do that. Yeah. Okay. So setup of imaging systems actually can be done using this.
Okay.
Okay, that's good. So now let us launch the race. So instead of time steps, the best practice is always to use path length. Okay. So just click in the time step specification. Use the maximum path length. Okay. And path length, we know that the focal length of this lens is around 100 mm. So of course we will do more than 100 mm, and this distance is around 20. So perhaps you can check with 150 mm. Okay. So length unit, I will just mention it as 1 mm, and this I can change it to 150 mm with a step of uh, maybe 2.5 mm. Okay, so it'll start from 0, then 2.5, 5, 7.5, 10, like that. It will store the results till 150 mm. Usually the ray optics model becomes very heavy because this because of storage of solution. Okay, so because each array is having 6 dependent variables, so it takes a lot of space for storing all this data. You will see in this model also it will take so much space. Okay, I'll wait for a few moments for you guys to add these properties of this ray tracing. So I've changed the time step as path length. Okay, and then length unit to mm, and lengths from 0 to 150 with a step of 2.5. So I'll just share that. Padmapriya, yeah, you are not audible. You can check perhaps your system once. Okay, and then just click on compute. So let us see how does it work. Okay, yeah. So here, so anyone getting this kind of results? I will just wait for some time for you guys to. Anyone getting this results like this?
Yes, sir.
Okay, good.
Yes, I am getting.
Okay, good. So here you can see that this focusing is happening somewhere over here around 100 mm far away, but you'll see a lot of other things as well. Now these other things are the secondary rays, that is because of this interaction with the glass material. There are few other things. So if you don't want to deal with those, just go to this geometric optics and make secondary rays, number of secondary rays as 0. And then compute again. You can go into the geometric optics and make secondary number of secondary rays to be 0. But those are not of interest to us. There will be some kind of course, there will be uh, some of this ray particles which will be reflecting because of this, because it's not anti-reflective surface. So some of them would be reflected, but the power of that reflection will be very less. Okay. Yeah. You can also create one animation, and you can see how the rays actually are propagating. You can export this image into a GIF file, and then you can see you can make some nice simulations. You can couple this into an optical fiber, for example, here, and you can see how the light is being propagated through the optical fiber because of total internal reflection. Some kind of couplers you can actually design using this. Okay. So any questions so far for this?
Uh, I have a question, Satya here.
Mm-hmm.
Can we use instead of let's say if we want to place a dichroic mirror where partial light would be
Mm.
go through and
Yeah, yeah,
part
yeah.
be reflected.
Yes, yes. So you can do that. So for example, first you need to make the light sources polychromatic, right? So you can go to from monochromatic, you can change to polychromatic, and what you want to specify, you can specify a vacuum wavelength. Okay, so you can change that into polychromatic. Then you go into the release from boundary, and now you can have an option of distributed function for the wavelength. So now instead of a single wavelength, I can actually have a again, there are a lot of ways. So you can have a Gaussian distribution of the power spectral response. So this is a spectral response eventually. So you can have a normal distributed values or list of values. So I can mention that it is actually a range of 400 nanometers with a step of 10 nanometers till 700 nanometers. So is the equal distribution. So I'm writing. You can also spectral distribution, like some kind of Gaussian distribution is also you can actually perform. So okay, some kind of normal distribution is also there. So here you can mention what are the number of values of steps that you want to have, and then mean vacuum wavelength, and what is the standard deviation of your uh, light source.
Nice.
Okay.
Yes. Okay.
Yeah, so right now we'll use this list of values. So now my light source is from 400 to 700 nanometers with a step of 10 nanometers, and they are equally having the same power. Okay, so now the power also needs to be incorporated. So if you just go to the right now, it's just the rate trajectories. So if you go to geometric optics, you can in the intensity computation, you can use something known as compute power. So now you have power also need to be given in the release from boundary. So now you can see the power is around 1 watt. Okay,
Ah,
and that 1 watt is distributed into this light source. Okay,
Okay.
and also distributed in 10 rays, so which is like divided by that 10 rays as well. So each ray would be having uh, so so around 10 rays would be there for 400 nanometers. Similarly, 10 rays would be there for 410 nanometers. Okay, so like
Okay.
that it is going to happen. And then to create this dichroic mirror, what you can do is that you can create one more uh, work plane. Maybe it's be a ZX plane. Okay, let's try to move after this guy somewhere over here, and I just try to rotate it.
Oh,
How do I rotate this guy? Or maybe I can draw that first and then try to rotate. So I make one square with 30 mm in the center. So I have this, okay, and then I try to rotate along the z-axis. So I just right click on the work plane and then just rotate to have an option of rotating. I go to more primitives or transform. Then I choose this and just rotate because I want it to be given some kind of rotation. So I can use 45 for example. Build all. Okay, it goes that side. No, not that. So the point of rotation should also be correct. So that would be point of rotation would be this guy is around how much. So I can just go to the geometry and see the using the measure operation. I can just choose this. So this is around 50 minus 15 and 15. So I want this point to be there. So along this this should actually rotate. So this is y is 0, z is 15, and x is 50. Okay, so this can write it down somewhere. 50, y is 0, and then 15. So I can just make sure that it rotates to 50, 0, and 15, and then I can make it 45. I think this should work. Yeah, you can see, right?
yeah.
You can make this minus 45, so it will actually work like this. So now now for example I can start with simple like mirror. Okay, so I will use a mirror operation and then just apply it to this boundary. Okay, and then let me just try to solve this first and then show you like how can it works like a mirror, and then I will go ahead and show you with the dichroic mirror. Okay, so now you can see that you're launching the rays from here. Okay, and it's now going through the lens and then it's interacting with this mirror and then focusing over here, right? But now here it's it is allowing the light through all the wavelengths. You can also change this color expression to the light source that we want. So instead of expression of t, you can actually mention it as a wavelength because now we have the light source. Okay, so instead of this I can have some kind of a spectrum. Okay, so they are actually together. There's no dispersive material, so you cannot see the difference. But yeah, they are all together over here. Okay. Now comes to the important part of applying as a dichroic mirror.
Sir, you
So,
had not,
sorry.
sir, you had not given any material property to the that square object at all, and
Yeah,
still
I've
it
given
behaved
mirror
like a
boundary.
mirror.
Yeah. You don't need to apply a lot of domain condition in ray optics. So basically, it's a game of interfaces. Right. For
It
example,
by
like that.
default took it as mirror, sir. Then
Here given a boundary condition is mirror, so it's just a, applying the equations of mirror. Just mirror. It's just reflection with wave vector direction. Just changing the wave vector direction. Yeah, you
oh,
don't need to
okay, sir. No,
apply
sir.
the.
What I mean to ask is the moment you created that square and
Mhm.
just did the orientation setting, the
Mhm.
properties got assigned to it by default. All of these to behave like
No,
a
no,
mirror.
no. The properties are of. There's no material property of this boundary.
Exactly, sir.
The
Yeah.
boundary is going to be act as mirror because I've applied mirror boundary condition.
Oh, okay, sir. Okay,
This is
you
a
did
boundary
that.
condition mirror. Yeah.
Okay. Yeah.
Okay.
Uh, so it acts as mirror on all the sides.
Yeah, correct. All the sides. Yeah. Okay. So one option is the reflection. So uh, let me see what other boundary conditions are there, which could be of interest to us. Material discontinuity, mirror, ideal lens, grating is also there. Okay, scattering boundary, no, release from boundary, black body, illuminated surface. Okay, from the ray detector, optical device. So here I can actually mention uh, this. What do you say? I can mention when it will actually work as 0 and when it will work as um, there should be a wall boundary condition to going to be. Yeah, wall is there, right? Yeah. So this wall is better. Yeah. So what condition I can apply? Okay, so it will be a, for example, it could be a disappear, pass through, uh, diffuse scatter, isotropic scatter, mixed diffuse and specular reflection, and general reflection. If you apply general reflection, it's like acting as a mirror.
Yeah.
Okay. So reflected direction would be primary ray condition, and then pass through eye condition, primary ray condition. Okay, pass through expression. What is that expression of this? So I can apply multiple ray boundary condition as well. Wall boundary. God, my system got hanged. Yeah, sorry. So this one, say I mention expression. If it is more than 500 nanometers or 600 nanometers, okay, it will pass through. Else, it will reflect. You understand, right?
Yeah. Yeah.
Yeah. So it's kind of working now as a diachroic mirror. Means I'm just trying. Transmittance is like 100 after 600 nanometers. Otherwise, it will like reflect. So let us try and see if it actually works. Yeah. So here you can see, right?
Yeah.
So uh, is allowing to reflect all these before 600 nanometers and just allowing to pass through after 6. So I can also make it like um, 650, so you can, it will be more prominent color that you will see. You'll be able to see this red light over here. Okay.
Mhm. Yeah.
So this kind of modifications you can do and then try to work with.
Yeah.
Okay.
Thank you so much.
Yeah. Hmm. Yeah. So now here it is like working as between less than for 450 nanometers coming over here. More than 450 it's transmitting. Okay. That's
For
good.
me, sir, this is Jai Krishna.
Sorry. Yeah, Jay Krishna, tell me.
For me, everything is transmitting.
For you, only thing is transmitted. Have you used wall condition?
Yes.
Same condition pass through with expression more
Okay,
than
yes.
4.
Pass through explosion at that one lab.
Yeah, otherwise specular reflection.
Okay, 1 minute, 1 minute. Yes, sir. No, sir, it is not like.
Can you share your screen? I'll
Yeah,
just look
sure.
into it.
So this is the condition one.
Okay, go down. You go down. Nothing is there. That's it.
No, that's
Okay.
it.
So have you gone to this geometric optics? Go to geometric optics.
Yes.
Okay. So here your intensity computation, you can make it compute power.
Okay.
Okay, and then instead of monochromatic, you launch the polychromatic light source. You're not actually using this polychromatic. No, in the top, you're launching monochromatic. You need to use
Okay.
polychromatic specific wavelength. Yeah. Now you go to release from boundary. Okay, and then you go down, and then instead of geometric, sorry, distribution function as none, apply list of values. Okay, over there you need to mention starting from 400 nanometers with a step of 10 nanometers and ending at around 700 nanometers. Yeah, just click play. Yeah, and then click on compute again. Then I think it should work. Not update solution. You need to compute again.
Yeah, sure. Got it. Yeah, now it is working.
Yeah. So it looks good, right? Looks good. Very good.
Thank you.
Okay, looks good. So anyone else uh, have any doubt, any questions about this modeling? Okay.
So what's the purpose you have used that sheet here?
This sheet is this boundary.
Yes, sir.
This boundary we have used as Satya Ghosh was asking about a dichroic mirror. Can you show me how can you model dichroic mirror? So I use added this boundary and apply a specifically a specific type of wall condition which actually worked as a dichroic mirror.
Okay, sir.
Yeah. So Sujay, is a question: is there a cost-effective way of using COMSOL after trial has expired? Uh, Cost-effective way.
So generally, it is a little costly, right? As a part of
Yeah, it's
university
cheaper
student, I
as
used to
compared
get
to ANSYS or
that.
any other optical
But the
tools.
university already has answers, and COMSOL is not there, and then asking for another tool might not be plausible for them. So is there a
Okay, okay.
student something? Oh, 6 months
This
trial version is available. Chetan is saying.
6 months trial. No,
Okay,
it's only
I was.
14 days trial usually they give.
Uh-huh.
Uh, yeah, and if you require, like we can request for extension for more 14 days. But other than
Uh,
that, it's very difficult. Yeah, you need to reach to
mhm.
your academic university and ask them if there is any possibility
Mhm.
to have this particular because of your requirement.
Okay.
Can they actually buy? Yeah,
Okay. Okay. Thanks.
yeah.
Sir, I have a doubt regarding the 2D FBG, wavelength domain analysis.
Okay.
Uh,
What doubt you have?
Sir, I have actually taken a longitudinal cross section of the fiber, sir. I
Okay.
have I have inserted gratings in the middle of the core, and then I have given the port conditions, sir.
Okay. Do you have your model with you?
Yes, sir.
Okay. But as you can, we can look into it 5 o'clock session in the next session. At five o'clock we start one-on-one discussion. That time you can just share your screen and I can look into the model. Okay.
Okay, sir.
Yeah. Yeah. So any questions in regard to the ray optics part?
Yes, sir. I have a doubt. Uh, So the wall condition you chose, now, can we make a wall with partially reflecting and partially transmitting? Like for monochromatic light, you chose polychromatic, then half
Mm-hmm.
wavelength is passing in half. Like
Mm-hmm.
we used to do in Michelson interferometer, we are using some mirror, which is not mirror, some glass which is partially reflecting and some part reflectance is some point one or something like. Can
Okay.
we
Yeah,
choose
yeah,
that?
you can do that. For example, here you can actually make the absorption. So maybe I will show you. Disable this and make one more wall condition apply to this one. So there are expression available. So you can make this pass through, okay, and then give an expression. So how you want to pass through, okay. So what is your condition? When do you want the light to pass through?
See, I want like half of the intensity should pass and half
Okay,
to
half of the
reflect.
intensity should pass through, right? Okay. So then you need to apply some kind of a, so you want 50% light to pass through and 50% to reflect, right? Sorry, to reflect, right? Yeah.
No.
Like
Mm-hmm.
a beam splitter.
Mm-hmm. Beams. But for monochromatic.
Yeah, yeah. That doesn't matter. How is it monochromatic or
Uh,
if you can make it for polychromatic, then definitely you can make it for
mm-hmm.
monochromatic, right? So here one of it could be like this one, for example. Let me choose monochromatic for simplicity to start with. So I'm mentioning here that 50% is going to get specular reflected and 50% will pass through. So I've written the expression of zero point 0.5 over here. Okay, you understand what I'm saying, right?
Yes, sir.
50% is going to get reflected and 50% will pass through.
Mm-hmm.
So if I'm sharing a 1 watt light source, zero point 0.5 light source will be reflected, zero point 0.5 will pass through. Is that what you want?
Yes, sir. Yes, sir.
Okay, so if you just click on study and compute, let us see what will happen. Okay, that is not happening. Let me just check it and see it again. Notice. E, what is expression? E, probability. Probability is, probability perhaps, correct, yeah. Yeah, or I have to play with the number of rays, actually, fraction of rays, yeah. Probability is 1. So the probability I give 50%, right? So now you can see 50% of light source is passing through and 50% is reflecting,
Yes, sir. Okay.
right?
Thank
So you can
you.
also, yeah, you can also see the power. So it's a ray power. You can see this ray power and then click on parts. You can see that total 10 rays are there, right? So now it is the rays, each of them is doing point 1. So here you can see 5.5 watt over here, zero point 0.5 watt is in going over here. Now, if you want, you can also give some kind of absorption coefficient of this particular boundary. So because of interaction of this boundary, there is some losses as well, right? If you write zero point 0.1, means there is a losses of around zero point 0.1. So now each ray that is going through, right? So it will lose around 10% of its energy. So now you can see that after its interaction, little bit less energy is being created.
But sir, this would be like 10 rays, 5 rays would travel reflected and 5 rays will transmit through. But
Yeah,
in real life scenario, it is like all the rays do have 50% transmittance and
yeah,
50%
yeah, yeah.
reflection.
Correct, correct. Yeah.
Is it
So
then? Because then it is like location possibility, location dependent,
correct,
right?
correct, correct. Yeah, yeah,
It
yeah.
is
This is one
then,
way to realize it. One other
yeah,
way, like
mathematically
each.
it is the same thing right
Uh,
now. But um,
no, no, I understand. So if it is probability is each ray, so each ray needs to have its own location base. I'm just thinking, can you do something like each ray you reach there, it should either 50%. So here actually the issue what happens what with what you are saying is that you need to increase the number of rays. Okay, so you are launching 10 rays, but at the end there will 20 rays. You understand what I'm saying? So we need to
Okay.
you need to have this secondary rays then. So something with that aspect needs to be done. We need to make this new rays.
But can we then, in this case, play with the mirror property? Not like 100% mirror effect, but rather than 50% transmittance.
Mirror is I don't think so. I don't know. Okay, let us try.
Like
Yeah.
if I see the benefit, so
Correct. Correct.
fabrication point of view,
Uh-huh.
if I have a if I, let's say, 200 nanometer aluminum layer would 100% reflect it, then 100
Mhm.
nanometer would have a partial reflection and partial transmittance,
Yeah.
right? Something
I
like
don't
that. I
know.
don't know.
I don't know. We can check it. I don't know. Yeah, this is not reflected. Yeah. It requires new rays to be created. That's the
Okay.
problem. Yeah.
No, it
Yes.
is fine. I just
Mm-hmm. No, that's a good point actually. Uh, okay. It is so far field auxiliary. So we have to create an auxiliary dependent variable for the new rays, and then we have to apply that. Then, if you want to also um, talk about the this thing, okay. If you want to make sure that the if it passes through as well. Which one was we mentioned? I don't remember. This one, right? Yeah. Yeah, but usually if in ray optics we don't worry about the location because we have to launch around thousands of rays.
yeah, that is also true.
So usually you don't worry about the location. Yeah. So one of the easiest ways to launch a whole lot of bunch of rays and then make them that half of it to pass through. Like this is also probability, right? So like
Yeah,
50%. So it
correct.
based on automatically it will be like it will pass through. So yeah, if you have a very large number of rays, then it will not be a big issue. Means you can still able to get it through.
And then there is also some sort of mirrors where you again, this is not my topic, so I am not very sure. But there are two edges, right? The front edge and the bottom edge. So, and then some reflection happens when when the ray passes through the medium and and it comes at the surface of the second edge, and it has
Sorry, can you come
yeah.
again? It passes through
So
the
so
lens.
let's say if the mirror is a little bit thick, the
Okay,
ray,
okay.
first of all, at the first
Yeah,
edge,
yeah, yeah,
it
correct, correct. No,
reflects
no,
and
but
then it
here we
travels and
assume that it's
then
a boundary. If you want to
yeah, yeah,
model that, then you have to model it 3D geometry with a
okay.
particular slab thickness.
Uh-huh.
Yeah, so
But
then
then
you
it,
will
it
see
comes
that
under this
particular.
ray optics only, or they
Yeah, ray
do
optics
go
only it
to.
will come. For example, you need to if even if you go and enable this um, secondary rays. Okay,
Hmm.
for example, I just use one. I launch only one ray. I can show
Hmm.
you. It actually happens with this lens. Maybe I need to use more number of secondary rays. Okay, actually it's in center, so it's very difficult to understand. Let me just make two rays. Two rays also becomes so difficult. So now if you see launching
Hmm.
this ray is moving. Okay, once it interacts with this guy, let
Hmm.
me just make this little bit more thicker. Okay, so if so now it is launching. Now you can see because of
Hmm.
this interaction,
Correct.
this
Yeah.
ray has come out, and here
Hmm.
also it has come out. Now it's interacting with the second boundary now, so that
Hmm.
also it has come out.
Once again.
Okay,
Correct.
yeah. So these things are already being captured. Okay, but
Hmm.
so here you can see this kind of in this second ray that is in come out will also interact with this
Correct.
front
And then
surface,
you
and
have
it's
once
going to
again
reflect.
reflection and
Yeah,
transmittance.
so this kind of resonating kind of structure is it creates inside.
Hmm.
It's unless until it becomes so everything is being captured, but this ray
Hmm.
is like the secondary ray are very low powered, so that's why
Correct.
usually we we remove it.
Neglect
We
them.
don't
Yeah.
consider it. But yeah, if you are required, then you can actually do that as well. Should not be a problem.
Mm-hmm. Thanks.
Okay, looks good. So, are there any questions? Otherwise, let us move to 5 o'clock last session. If you have any discussion to do. Okay. Thank you. Then let us meet at 5 o'clock session. If you have time, you can fill that feedback in assessment form. Yeah. Thank you. Hello and welcome everyone. So let me know if you have any questions.
Sir, hi sir, Chetan here. I wanted to know if 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 we can do metalens kind of simulation in COMSOL. Generally, I've tried uh, doing profiles for meta atoms, individual meta atoms on ANSYS numerical last time, and I was able to do all that. But the problem is taking from meta atom to arrangement to form a meta lens is a bit of a complicated process in ANSYS. The workflow is a bit complicated. So, is it possible, because COMSOL is just a single interface, so is it possible that I do meta atom analysis and then slowly build the entire meta lens based on a specific formula of arrangement of those meta atoms?
Yeah, if you have something like schematic or something to show, it would be better.
Oh, okay, sir. It is actually here on my workstation. I'm in a different location, but maybe I'll share it next time. But it is possible, right, sir? We should be able to translate from meta
Yeah,
atoms to metallets.
yeah.
Okay.
Meta atoms. I don't understand what is meta atoms actually.
As in, sir, a metallens will have all the structures, like let's say some pillars of geometry or any spheres of some. So that's one specific pillar or that one specific uh, structure on the meta atom is called a, sorry, on the metallens is called a meta atom.
Okay, okay, I
So
see.
they are arranged. The profile is arranged on a
I see.
maybe, yeah, spherical
Yeah,
surface
yeah,
or a
that should be
circular
possible.
surface.
Yeah, yeah. I thought same you're doing more atomic simulation, something like that. Okay,
Oh,
yeah, that should be possible. Yeah, yeah, yeah.
okay. Maybe sir, if you come across any such video tutorial or material, you can just put
Hmm.
it as a link maybe later.
Hmm. Yeah. On top of my head, I don't have. So what we had this. Uh, if I will just try to share my screen and search. We wrote on this kind of pillar kind of structure. We wrote one, but it was an absorber. So it's kind of a. What is the objective of doing this? Is working like a filter or something like that?
Yes, sir. They can work as filters, as absorbers in a certain band of frequencies, or they can work as filters also of various kind, whether notch or band
Yeah,
pass
yeah,
or
yeah, yeah, yeah.
applications.
So we actually worked on this anti-reflective microstructures for this kind of pillars we developed. So instead of
Ah,
this
yes, sir.
model like,
Something like this.
mm,
Yeah.
yeah, yeah. So we actually model in 2D, try to understand the bulk silicon and rectangular structure like pillar on this. What does it actually work? So bulk silicon actually reflected a lot of light. So we're trying to make an
Ah,
anti-reflective coating. So actually
mm,
make a pillar kind of this structure. Then actually it allows the light to pass through even for more angular incidence, pyramidal kind of structures. If you put it
ah,
on the bulk, then also it actually helps. So I think this would be a good place to start with and go through
okay.
this blog. Yeah, this is kind of not much difficult in COMSOL. Yeah, should be possible.
Sir, in on that very same page that you just yeah, sir.
Hmm.
If you go on the top, uh, the middle image kind of shows on the top the middle image, exactly fully on the top, sir.
Okay,
This page.
this
Yeah,
one.
exactly.
Hmm.
The middle figure shows how you're trying to make a lens out of just on the right hand side. That we call it as a meta atom kind of a
Oh,
thing.
okay, okay.
Just
I see.
one
I
side.
see. Uh-huh.
Yes, and
Yeah.
then you are using it and arranging in a certain fashion.
Hmm.
Now, when you are arranging it, the arrangement can happen in a way such that every pillar there may have a different radius, a different height, and the arrangement will
Okay,
happen such
okay,
that you get some confocality once you arrange in that particular fashion. It
okay.
can become a confocal kind of a lens or anything, maybe used for aberration, elimination, or something like that. So
Hmm.
that arrangement of microstructures is where it gets complicated a bit in ANSYS. So that
Yeah.
so
No,
can
but
we have
this
such kind of
arrangement, like, are they getting repeated this arrangement, or it's like completely random, or like, or how it is?
no, so there is a specific formula that we need to feed in to have this
Mm-hmm.
arrangement. For example,
Okay.
when I know that the lens should meet a certain criteria, let's say this much focal length and this much, let's say, uh, So generally it is on focal length on the diameter f and d. Once you specify these two, ANSYS kind of self calculates where to place the meta atom and with what geometric changes does it has to place the meta atom.
So
So
that
it does
equation
it
you've
by
written in ANSYS,
uh,
right?
yes.
That
So
equation,
we
yeah, yeah.
kind of yeah. So I was thinking if COMSOL can do this
Hmm.
kind of things.
Yeah. So that should be possible. Like what we did with the geometric part lengths, right? We just need to mention a
Yeah.
focal length, and based on that, it actually changes. So you can write
Mm,
this your equations, variables, and based on that, change the geometry based accordingly
mm,
to the height and all. So here we actually, if you see in this block, we actually optimized the geometry, the
mm,
thickness, the length of this pyramid structure, the length, the width, everything we actually optimize. So here, this is the
mm,
optimization.
mm,
So thickness of the
mm,
pillar, height of the pillar, so that what is the optimized geometry parameters, right?
mm,
So those things we try to do. So what is the optimized, so that you actually get a higher transmittance. So this is a
mm,
optimized geometry, so that it's more
mm.
than 95% reflectance, transmittance. Otherwise original geometry was like very around 82%. Okay, similar to this one, if you see. So I mean, this is like for optimize, but I'm saying the same thing could be done for a equation based geometries as well, for a bigger structure in 3D modeling. Also, you can do it. Go ahead. It should
Okay,
be
sir.
possible in terms of,
I'll go
yeah.
through the I'll go through the page.
Yeah.
Thank you.
Excuse me, sir.
Yeah.
Sir, I'm Jansi. Sir, actually, yesterday's model I tried with water and the silver. The enhancement came out to be up to 60 for a distance of 20 nanometer. The thing is, I
Okay.
want to add now, as you said, component wise prisms. Like now, I want to go for 2D. So when I'm doing 3D model of sphere, how can I add component of triangle in 2D? Or should I make it
You
that
need to use a
also?
polygon. You need to make
Okay.
polygon and then just mention the coordinates of each vertices.
Okay. And yeah, one more thing, sir. So this
You can
parametric
see this example
sweep.
that I've shared some time back, right? This pyramid I have shared some time back. This pyramid, right? You can see this example. I think I've shared here as well, right? Sometime back. Yeah, this
Okay.
blog is there, right? So this pyramid I have made. This is also triangular, right? You see, you open this model and see how I have done it.
Oh, yes, yes.
We've done it,
Oh,
yeah.
yes,
So
sir.
that would
I'll
be
go
helpful.
through it.
You can go to this MPS file in the end, get the MPS file, and then you can do they have it or they have removed? I don't know. Yeah, they have it still now. But this product MPH file is not there. So you can ask them perhaps to, you can write to the support and they can help you to get this MPH file. Yeah. Okay.
Yeah. So
Or you
one more
can, there will be
thing,
some
sir.
other ways to do it. Yeah, should not be a problem. Yeah.
Actually, in your previous sessions of ISTEM, you told about Polygon, how to use. Can I use that
Yeah,
drawing
Polygon you can
thing?
use. Yeah. Polygon is a way to do for a lot of things. You can, any structure you can create using Polygon. Just the vertices of each point you need to mention.
Yes, sir. So, this parametric sweep for position. So I am not getting clarity of how to actually do this. I understood the distance, that position. Can you please explain, sir? Like,
Yeah. So what
if
exactly
possible.
you want to know?
Like you told the coordinates we have to choose and all. So how is like what is the procedure and where to choose the coordinates in the geometry we have to choose or something like that. I'm not having a clarity of that or something.
Uh, Yeah, so by geometry, I mean the coordinates, for example, yeah, I can just show you how to do this simple thing. So I'm not adding any physics. I'm just trying to make one geometry and just show you how you can do a parametric sweep so that it kind of feels like it is actually moving. Even I can even do a 2D geometry because it will be more simpler. So for example,
Yes.
I create one circle, and here I can write x1 pos y1 pos. Okay, and here I can define what is x1 pos as 0, y1 pos as 0. So now this circle is defined at the origin. You understand? Now another particle I can
Yes,
have
sir. Yes,
duplicate
sir.
it, and here I can write x2 pos and y2 pos. So this x2 underscore pos would be like 5, and y2 underscore pos would be like 5. So now if you go, so this is how they both are located. Okay, you understand, right? These are defined by its coordinates
Okay.
now. Okay, now what I can do is that I
Okay.
can actually add one study, any kind of study, and then I can do a parametric sweep. Okay, and here I can apply all 4 of them. Okay, so here is first starting is 0, 0, and 5 and 5. This is my original position. Surface plot, if I do, I think it should work, right? This is my original plot. Now I can do one more, that now it is moving to 1, 1, and this guy moving close by. So I just, so now I have to done with specific parametrics. Yeah, yeah, yeah. So specific combination organ parametrics. Yeah. No, specific combination you can put and click on. Okay, fine, no problem. Thank you. So now we can say this is the parametric solution, and this is for the uh, first position, moving away, then very far away. This is for the very close by. You understand, right? Yeah, close, coming close. Like this, you can keep on adding the parametric sweep more and more, so that it actually comes by and then moves away. For example, there are two solutions now. Original position, then next position. Like this, you can add. I hope that answers your question.
Sorry, sir. In between, my network was gone, but I will see the recording. Yes, sir. Yes.
No problem. Yeah. So this looks good. Sure. Any other questions?
Hello,
So
sir.
can
Yeah.
I share my
Pratik here.
screen?
Mm-hmm.
Yeah, sir. Actually,
Yeah, yeah, yeah. Who is there? I don't know. Pratik, you are there, or
I'm.
yeah, Pratik. Yeah, tell me. Then I will.
Yeah, actually, sir. Yesterday you have told that how to put the piecewise function. Like I'm telling now how the graded index fiber.
Okay.
So here I want to if I want to give some refractive index gradient from the left to right, like not from the center, then how we can do?
I don't understand. So can you share me some kind of schematic of what you're saying? Can you quickly make one schematic?
Schematic, yeah. Schematic means just you just. Achha, okay. I'm sharing. Like,
Yeah, yeah. You can make it in Paint, for example, so that you understand what you're saying.
no, I'm just sharing the COMSOL page. Then I can you can understand.
Mm-hmm.
Actually, you can see my slides. You can
Yeah.
see my screen. Yeah. Actually, from that point to that point, I want to give a refractive index gradient, like uh, increasing or decreasing.
Yeah, the same thing is mentioned in that Lundberg lens, right? So have you tried that out? Have you seen that model?
Yeah, I've seen.
So did you try to
They,
implement that?
no, actually,
Yeah.
I cannot understand here. I mean, the variable we can put or
Yeah, you can use the word variable, and that variable you can define it in the definition section. Okay.
okay.
So what my suggestion would be that you take a printout of the Lundberg example, like that document. Take the whole
Mm-hmm.
20-30 page document printout, and then step by step do the whole process from scratch. Okay.
Okay.
Go to that painful process, and then only once you do it, now then you will understand how they are doing it.
Okay.
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 So yeah, that is the way to go.
So one more thing, just uh, so actually, just I'm just seeing your paper on an example. Like there is a meta surface thing.
Hmm.
So there they are giving some light and reflectance. So here they have choose some port at the same position or like port 1 and port 2.
Hmm.
So
So
they
what is
are.
the question?
My question is they have taken the reflectance of there, but where you in the for the second day you have done for port 1 and port 2 at the transmitted one, and take the S21 and S22 parameters, reflectance and transmittance.
Okay. So what is the
So
question? Yeah.
in this case, how they can take reflectance by only
No,
S21 or
here you need to so if you see on the right hand side. So that is the actual
yeah.
model. I think that's what they have made. So that's
Mm-hmm.
some kind of block of geometry that they have created, and from the top they are applying port condition in the top, and then another port in the bottom. Okay, but they
Okay.
are using angle of incidence. That's what they're making from theta. So this
That
is some kind of so that's how means it needs to be done. So just make the same model that we have made, but angle of incident you need to give some finite value, and then see first that because of that angle of incident is there some angular plane wave is there or not. All those
mhm.
things you need to see
No,
this.
and my question is actually instead of taking the port 2 at the bottom position, if I take the port 2 at the same
No, you
thing.
don't need to multiple ports to the same boundary, right?
Okay,
Means
okay.
unless until there are some higher order modes being generated. So here on the top single port you can if you apply single port in the top and bottom you apply PML for example, then you can use you can get reflectance like what I think Kavita was showing tomorrow yesterday. I don't know if you've seen that, but yeah. So if you apply PML top port and then don't apply anything, so whatever is just passing it will just absorb in the bottom.
Okay, sir. Okay. Thank you.
Okay, so
Sir,
that
I have a
reflection I
doubt.
think that's one. Yeah.
So the section you have shared for the FPG, actually there is the grating for the entire domain. In the case
Mm-hmm.
of fiber Bragg grating, we have the that what should I say, that section for a limited length. It's not for the
Mm-hmm.
entire core.
Correct.
So how can I do that? How can I design that FPG?
That then you have to have to make that fiber with finite number of grating. The whole thing you have to prepare then. Yeah,
So
there is
can you
no other
please
way.
elaborate a bit?
Elaborate means yeah, I can share my screen. So in most of the example, what you will see is that you have this fiber, and then this grating you're talking about, right? This is N1, N2.
Yes, sir. Yes, sir. Yes, sir. This is
Yeah.
actually I'm talking about. So the middle portion is empty. It's not completely filled. The refractive index of core is same as the middle portion. The refractive index of the slit you have
Mm-hmm.
drawn in between, it has different refractive index. In between, we have the same refractive index as of the core.
Okay. Yeah. But usually, what you will find is that means how many number of repetitions are there?
Um, it's up to us that generally it's 10, 20, 30.
Yeah. Then you can make the whole structure means like this, and then excite the structure over here. So you apply P1, this P2, like that you apply, and then you can see the structure.
Should I make it for the entire geometry?
Uh, Yeah, means you can see means how it is. Either you can use. I actually don't understand. If you can share your
Yes,
screen
sir.
like
Yes,
what
sir.
you're
Yes,
explaining.
sir. Actually, let me share. So this kind of structure I want to design.
Which kind of structure?
So this
There are a lot
yellow
of
one,
structure.
this yellow
Okay.
one.
Okay. I cannot see your mouse actually.
Okay,
The
just a
Terra
second.
Zion. Okay, this one. Terra Zion one.
What is fiber gradient? The first one. Yes, sir. Terrazion.
Okay.
Yes,
Okay.
yes, 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 sir.
Okay. So yeah, means I think you can do. So what was the question? Can you come again?
How can I design it? I'm still at the designing part, sir. I'm not able to design it correctly. I'm not still able
Yeah.
to see the
So
transmittance
what
and
you can do is
reflectance.
that you can first make this longitudinal cross section.
Huh.
Okay, and then you can model it. The complete structure should not be a problem.
So first I should make it for the entire geometry, and
Yeah,
then I
yeah,
should reduce the numbers, and then I should go further.
yeah. You can keep the same numbers as well. Means yeah, ideally it should be like first make a simple core,
Hmm.
see how the wave is propagating or not.
Hmm.
Then
Hmm.
add a single layer, then two layers, and then go on increasing the number of layers.
Okay, sir. Okay.
But this longitudinal cross
Okay, sir.
will not be much difficult. When
Okay, sir.
you do in 3D, then it is going to be difficult. Yeah.
No, sir. Currently, I'm doing it in 2D.
Mhm. Yeah, yeah. So that 2D should not be a problem.
So first I should design the entire geometry, core and cladding, and then I should put a single slit,
Yeah,
then another, and
yeah,
then I
yeah, yeah,
should
yeah.
see the
Correct,
variation.
correct, correct. Yeah,
Okay, sir.
you
Okay.
should be able to do it. Should not be a big problem.
Okay, sir. Thank you so much, sir.
hmm
And sir, what should I do first? Observing its transmittance and reflectance.
As you're applying ports on both the sides, you can use
Mm-hmm.
S parameters.
As per the same absolute value of the S11 square.
Yeah. Mm.
Okay. Sir, can you please explain a bit how you have chosen in the second case you have chosen S31 and
That was a higher order
S32?
in higher order, but in this case there are no higher order diffractions, so
Hmm.
you don't need to worry. So you will get only S11 and S22.
S22.
S21, yeah, this two means two. The matrix would be S parameter matrix would be S matrix would be only by 2 by 2. Don't need to worry about it.
Okay, sir. Okay. Thank you, sir.
Mm-hmm. Yeah,
Hello.
Ayushi, you were saying something.
Yeah.
Yeah, you were sharing
Yeah.
your
Can
screen.
I share my? Yeah, I'll share the schematic also. Yeah. Mm, yeah. So, so can you see?
Yes, I can see.
Yeah. So basically, we have. Okay, I'll show you one more. Yeah. So this is a picture. So we have a nitride membrane, and on top of the top surface has this gold pattern, and on the bottom we have another gold pattern that is this. So these are the layers on top and bottom of the
Mm-hmm.
nitride. So how do, and this is repeating. So how do we design that and in COMSOL, and when we try to take this nitride membrane, how do we define this? Like, you know?
So basically, it's exactly the same way the example that I shared some time back of metamaterial graphene that was modeled,
Graphene.
right? So you can
Mm-hmm.
use that same way. This is one more example I can share you. It is not of multiple layers, but at least one layer. So frequency selective surface. So it is very much similar. Selective surface. So nitride layer is, I think, it you can model using a what do you say, some material, glass material. Okay. So here you can see This is a case of frequency
And we can
selective
change
search.
its refractive index.
Yeah, it's just refractive index. You can put the real part and imaginary part, whatever you want to put based on any. You can see if it's available in COMSOL. Else you can input whatever you want. So this is a structure you can see, right? This is a slot actually.
Okay.
This is a copper structure, some conducting metal. But in the bottom also you want to apply now. Okay. So
Yeah,
yeah.
right.
So then this is a very much relevant example. So I'll share this with you.
Yeah.
You can go through this. It's exactly what you want. So this is using EMW, that is RF module, but this could be same model using wave optics as well. So I think this is with wave optics RF module. This was wave optics. I think I shared it with the wave optics one only. So it will be so you can model with RF as well as wave optics. What you said, right?
Okay.
Yeah. Basically, you can use a TBC, transition boundary condition, to model the gold bottom and the top, and the nitride is a dielectric material like silica glass that we used to apply like that. It would be some kind of a dielectric material, dielectric slab. And the
Okay.
bottom and the
So,
top is air domain, right? In your case,
right.
yeah, yeah. Then it should be straightforward.
Sure.
Mm.
Okay. I'll try.
hmm
Good evening, sir.
Yeah.
Sir, please suggest me regarding laser tissue interaction for heating the tissue. I want to understand the temperature distribution when laser incident on the tissue and how laser
Yeah.
parameters like um, pulse duration, wavelength of the laser affect the tissue temperature distribution.
Yeah, so you can see this example, laser heating of semi-transparent material. Okay, this is a good and laser heating of a silicon wafer. So using this events interface and also modeling of a material via Beer-Lambert law. So specifically, we are looking for the Beer-Lambert law, right? So
Yes, sir. Yes, sir.
yeah, so basically, this is what you can go through. Few of the references I'm sharing. You can just go through that. Okay.
Okay.
I
Okay.
think this is a new thing that has come. Yeah. So I think here this is also a blog actually on Beard Lambert law, how to model this. So if you're interested, you can so uh, how the heating happens through this. So I think they have used this. So this using general form PD, you can write your own equations actually. So I think he's written his own equation. But now I think we have its own um, library. So here pulse heating of a semi-transparent material, right? So
Okay.
this also is a very good example. Okay. Was recently, this is just last year published, right? So
Hello, sir.
here they have used radiative beam absorbing media.
Okay.
Yeah, so I think this is what you can use in this case. I'm just getting a call. Just hold on.
Hello, sir.
Yeah, sorry. Any more questions here?
So this is Jay Krishna.
Yeah.
Hello.
Yeah. Who is Sabita? You want to ask first? Yeah.
Okay, sir. Okay.
Yes, sir. Sir, can you suggest me any tutorial on how to include nonlinear optical process when light pulses interact with any medium.
Interact with?
Any dielectric medium or conducting medium,
You
mainly
want
dielectric medium.
non-linear effects, some kind of non-linear effects you want to model? Okay. So
Yes,
actually
yes.
we wrote one blog. I don't know you've seen that or not, but it was an old blog. Yeah, if you're interested, you can go through this blog. I can share it with you. Oh yeah, but a little like 2018. The first order, second order, third order
Oh,
non-linearity. It gives a basic introduction to model all these non-linearities.
okay.
Okay, it's not a kind of a foolproof thing, but yeah, it's just a tip of the iceberg of what could be modeled.
Okay.
Okay.
Sir,
Yeah. Hi. Yeah, you wanted to share this model, right? Something you said sometime back.
yes, sir. The FPG, 2D FPG model, sir.
Yeah, you can share the screen. Yeah. Meanwhile, you share, Jai Krishnan,
Yes,
you had
sir.
some question, right?
No, I just want to
Regarding, yeah.
share a model. Actually, I have done it.
Oh, so after this, she shares,
Yeah,
then you
sure,
can share,
sure.
no problem.
I'll wait.
Yeah.
Sir,
Yeah.
actually I have modeled the longitudinal section like this, sir.
No, I cannot see your screen.
I cannot see. 1 minute, sir. Sir, sir, could you see, sir?
Yes, I can see now. Yeah.
Sir, I have given geometry like this. Like I have taken a rectangle core and cladding, and then small rectangles for grating.
You can show the materials actually. That way, it is more better to understand.
The
Yeah. Can you
material.
close that study node and add physics, add study?
This got blank. I don't know why
Can you
this.
click on reset desktop? Perhaps that will help. Perhaps. Yeah. Not helping. I need to get some other like click on geometry once.
Might be showing the mesh, very dense.
You're very optimistic, Sujay.
Okay.
No, I think there is
Not the
something
nicest.
to do with this graphical issue. So what you do is you relaunch your model again.
Yes, yes.
I don't close it. Okay, but you have closed it very fast. Ah, this is good. Yeah.
So this
This.
is the other one, sir.
Okay. Yeah, like file open is kind of very fast.
Sir, actually the thing is, uh, I I don't know like if I have seen this structure from I got this structure from some of the papers, but the papers were not like they didn't give the full. I didn't get the answer. What to how to calculate the reflectance versus wavelength plot. I could only do the boundary mode analysis. Sir, I'll show you the materials.
Now you just need to click on reset desktop.
Uh, this one I have. This is a course.
Hmm.
I have taken. I have given this n
Yeah.
value
Can
from
you
the
click on
parameters.
material 2?
So material two is the
Okay. Can you
grating.
click material 3?
Three is
Okay. Can
this.
you open this electromagnetic wave frequency domain?
Yes.
Okay, you in port 1. Can you click on port 1? Okay. How are you? What are the mode fields? No, no, go
Sir,
down.
actually, what happened is I
Periodic.
need to get
Periodic
the.
might not work actually here.
Yeah, yes, sir.
You need to use numeric. Yeah.
Numeric, but with numeric, I couldn't do the this wavelength domain analysis.
No, you can do with numeric as well. Yeah.
I'll
So
just.
yeah, but what is the mode field that you are showing? Means what is the polarization that you are launching with in port 1?
Uh, Polarization, T,
Yeah, mode
electric.
field, electric mode fields
Yes,
of
sir.
your port 1. Can you go to the port 1?
Yes, yes.
Yeah, go down in settings. Okay, because this is numeric now, it not be there. Yeah, go to port 2 now. Yeah, here also make numeric port, but yes, 000, right? It should not be 0. But yeah, and you make it numeric and then try to model using boundary mode analysis. Okay, then it will work. This diffraction.
Boundary mode analysis.
Mm.
Yes, sir. I'm able to get that, sir. Boundary mode analysis. But I'm not getting the plots of transmittance and
Yeah,
reflectance.
so for transmittance, so what have you done?
This one's a boundary
Uh,
mode analysis.
so here, okay, this an effective way of okay, what is mode analysis 2?
Two I gave grading.
No, but here both of them should be the same mode index. That is a core refractive index, whatever is the one you mentioned for the core.
Oh,
Okay, and then are you doing a frequency sweep or wavelength sweep?
no, sir.
Yeah.
Frequency sweep I'm not doing.
Yeah, so you need to do a wavelength sweep or frequency sweep. Okay,
So,
only then you will be able to. No, don't do it from here.
okay,
And I
sir.
showed you. I don't have you seen that. If you right click on the study too
Uh,
and add parameters, parametric sweep. Okay.
yes.
Yeah, in parametric sweep, and in that you can sweep the lambda from what wavelengths you want to work with.
From 1548 nanometers to like
Yeah.
1500
So
nanometers to
yeah, so here
1600
you can
nanometers.
mention that. Okay, and then you can plot 1D plot group using global plot S21. You can plot absolute of S21, that is transmittance,
Oh,
and reflectance is S11, absolute of S11. If you see the recorded videos, you will see how I have done it. I've done
okay,
it
sir.
yesterday for this wavelength sweep, so you can see how we have done this wavelength sweep. Same thing we have done, so that should be possible.
Okay, sir.
Okay,
Okay.
should be
Thank you,
possible.
sir.
Yeah.
So this was the design I was saying. This is exactly same what I was asking for.
Yeah. So that's what I'm saying. So you need to do this 2D longitudinal cross section. Then using port condition, using numeric, you can actually launch. I think you have already launched it, so it would not be difficult for you. Yeah.
Okay, so I'll do that.
Hmm.
Sir, so one other question I have, sir. Sir, I'm aiming to model a tilted FBG, sir.
Okay.
So I need the cladding mode resonances, both the lower order cladding mode resonances and higher order cladding mode resonances. Uh, so, would I be able to do it with the help of boundary mode analysis?
Yeah, same approach remains the same. Just the geometry keeps on changing.
Uh, Actually, I need the cladding mode resonances, which will be so. I need to take the clad, sir, for boundary mode, refractive index of cladding.
Sorry, can you come again? What is the question?
So when I consider the tilted FBG, there will be the some of the light gets coupled into the clad, and I need those cladding modes. I
Okay.
so I need to uh, I need the cladding mode resonances and the the trans core trans core mode transmittance. So I the refractive index value, which value should I take, sir?
It has to be always the mode search index would be always around the core refractive index. Okay, and this approach would be very much similar to the one that I'm sharing you right now, dielectric slab waveguide. Just do the ditto same approach. Okay, and then keep on adding the diffraction grating one by one. You approach the same model that I mentioned. See, you use the same thing using the port boundary mode analysis, and then add a grating in the bottom middle, and then keep on adding grating. Whether it is tilted or normal direction, approach everywhere is the same. If you want to do some resonant mode analysis, then you can also do this eigen frequency analysis. That will help you to do this modes, resonant modes.
Okay. Okay, sir. Thank you, sir.
Mhm. Yeah,
So can I share it now?
yeah, yeah.
So can you see this? Hello.
Yeah.
So this is my structure that I'm working on actually. It's a distributed drag reflector DBR with high and low index refractive index material. So I've defined the parameters here. Can you see those parameters?
Yeah.
So this is the parameters I have taken up.
So what is the question, Krishna?
So the thing is, I'm getting the reflectance curve like this, sir. I'm getting it properly for the DBR.
Okay.
So I have used a port condition.
Yeah.
This
So what
thing.
is the question?
So my question is, on top of this, the high index material, I have to add a gold like this.
Gold material.
Yeah, gold. I have added that as well. So you can see me here. So this is my gold, this domain.
Okay.
Then what conditions I have to use? I use the same conditions actually. Periodic condition, the port 1 and port 2 same, similar. Everything is similar. So what I got is, this is the result that I got. The green line, that is the reflection that I
No,
got
no,
actually.
but yeah. So do you understand what is happening? Deflection is zero with this
Yes, yes,
gold.
which means no reflection. It is completely
So what
absorbed.
is transmittance is full
Yes.
transmittance means? I don't know. So, but this is a the way. So if you go to this model with the gold, so you open the electromagnetic wave frequency domain. So you're applying port condition to the gold, right?
Yep.
This is not the correct way to do it actually,
Yeah, that's
because
what I don't
there
know
would be
what is
something else, right, before
yes,
gold,
yes.
or like air domain. I don't
Okay.
know how in the reality how does it look like. Is
In
there a
the real,
dielectric domain in front of gold, or it's like that is the
no,
first domain,
that is the first domain. Either it is air. Mostly it is air.
air? So you add one air domain, and then instead of modeling this gold structure, you apply a TBC,
Okay.
transition boundary condition. Okay,
Okay.
because with this you need to also consider this. This meshing to be skin depth and all those things you need to find whenever you're
Okay.
modeling a 3D geometry or domain geometry of a many metal material. Then this meshing is required to be brought. So what was the question? Come again, means what? You're getting the green line, you are showing its reflectance is almost zero.
Yes, I should get a peak in this gap actually.
Oh, okay, okay, yeah, yeah. So that's what
Get a
means.
peak.
Yeah, that is correct. Yeah. So this approach is uh,
Only I
I don't
have this
know.
issue for a long time. I don't know exactly what to do. You define this as wave equation electric. I have created another domain, and I
Yeah.
included this by LD model as well. But for that also, I'm
Mhm.
not getting anything. I don't know exactly
Mhm.
what to do.
No, you can use this transition boundary condition and apply in the top of this of this
I,
structure. Yeah,
if
yeah,
I
yeah.
create
This
an air
structure, correct.
domain, if I
And
create an air
apply yeah, and then apply air domain on the top. Okay.
Sir, this is actually a thing called TAM plasmons. That plasmon will exist in the interface between the gold and where exactly I have selected now.
Okay.
So here only that plasmonic state will be existing.
Okay.
So that is what I want.
Or
So I have to
or what you
upload it.
can do, you can keep the gold, just add one air domain in the top.
Okay.
Okay, so then the port is given to the air domain, because if you
Okay.
go in port one condition,
Okay.
you're giving what, numeric port?
No,
No,
no, periodic actually. For
periodic.
periodic, for
Okay, okay,
numeric
yeah.
also, I'm getting the same results.
No, no, yeah. If you go
Have
down,
boundary mode analysis. What's it?
yeah. If you go down,
Okay.
okay, yeah. So the refractive index also you have to put na, so it's very difficult. So you put one air domain and then you make a gold domain then. then you
Okay.
keep all the structures same. Next
Okay.
you put air domain and then TBC and then see the structure same. Then see how much difference are you getting.
Okay.
Okay.
In the
Or also
current.
addition, what you can do is that
Okay.
keep the same geometry what you've done before. So
Okay.
what was the original geometry? Can you go? Which was
This
working? The
the
top one.
okay. This
Component one. This
1
one.
minute. Wait. This one, sir.
Is that a
Why is
component one? No, component
yeah.
one I'm asking.
Oh, sorry. Yeah. This is
Yeah,
the
in that go
component.
to material section.
Okay.
Yeah, material one. This one, right? So what you do is that you apply TBC and somewhere in the middle,
Okay.
right? To see how is that gold affecting TBC?
Okay.
Change or happening or not? So if you apply
Okay.
gold, what is the change that you think will happen?
The thing is, I should get a peak like here. You can see the band gap, right, from
Yeah,
1.2 to around 2.1. So
yeah.
between this gap, I should get a dip in the reflection. Only that one has to be like
Okay, okay.
a
Yeah.
it's particular wavelength.
Mm-hmm.
So I should
Mm.
get that. But since these in the DVR, it will be dielectric, both the materials. But when I'm adding the gold, I don't know how to define the gold, how to make sure
Yeah,
to make COMSOL to understand that.
yeah. So
That is the
yeah,
only.
you can just try out multiple this different variations.
Okay.
Yeah, first try to apply some TBC in the middle, see what is the
Okay.
difference that is happening. Okay,
Okay.
and then slowly try to add some air domain in the top and then put it. I think
Okay.
this should be solvable.
Yeah.
Yeah, it should not be a problem. But only a port condition directly to a metal I've never seen. Port
Okay.
condition is always you can give an air domain and then whatever you want to put.
Can I use SBC scattering boundary condition instead
No,
of gold?
SBC doesn't make sense. Yeah, but it doesn't help you to find scattering parameters. So I don't know how will you find transmittance then or reflectance.
Okay. Okay,
Okay,
sir.
that's
Okay.
good. Yeah,
Okay. Thank you.
okay, thanks.
Sir,
Yeah.
Sujay here. So there is a, I am still in the thinking part of the problem, but there is a femtosecond, high power femtosecond laser with 100 megahertz repetition rate, and the peak power goes very high until 30-40 kilowatt. The goal is to do dispersion management and nonlinear effect study on the fiber coupled laser. Now, like when the source is such a precise one, do you do some sort of other setup changes, or how do you approach this?
Sorry, I couldn't fully get you. Means you have a very high powered source and femtosecond laser pulse. So what is
Correct.
your application?
So the goal is to delay the pulses. So the pulse width would be on an average 50 femtoseconds, and the application is you need to delay the pulses uh, from anywhere between 10 femtoseconds to several thousand femtoseconds. And because we want to delay it, we want to study the dispersion effects and also the non-linear effects, because the peak power goes to really high values, and I am not very confident
So
that all
delay
kinds
means
of
on what basis will it delay? Delay means you want to change the on off period.
we want to change the when the pulse is moving towards from source to detector, we want to delay the signal and do the measurements at multiple time
Okay. So your question is
stamps.
how do you introduce delay in COMSOL?
One thing is that, and also the when the source is such a precise. So how does anything change when I have a femtosecond laser source, or
No, so your question first is that how do you model femtosecond laser source in COMSOL, right?
yeah,
Yeah,
the
this is a
source?
temporal Gaussian function kind of a laser source, like it would be.
Yeah, you can say, yeah.
Yeah, so it's the same example that I shared sometime back, plasmonic hole array, right? It
Okay.
actually has this temporal spatial Gaussian light source, its models. So yeah, I will
This
share it with you.
plasmonic. Okay.
Yeah, I mean, the application is different, but you can see, you can learn
Yeah,
like
yeah,
how
just to get
they
some.
have
Yeah.
modeled this temporal Gaussian function. It's also femtosecond pulse.
Okay.
So it's a 2D model of it's complete time dependent solution. So
Okay.
it takes some time. It's a very smart way of
Uh,
modeling this. So you can learn how to model this femtosecond light source from this model.
okay.
Yeah, actually, this uses I think SBC to as a light source. actually.
Okay.
Yeah, the
It
SBC could
looks
also
like
be
that.
used as a light source. Actually, some boundary condition it has used. I don't remember exactly, but
Mm-hmm.
it is. Yeah, you can do that as well. Yeah, just
Mm-hmm.
writing a um, kind of a equation. But earlier it was equation. Now I think there is a feature of releasing Gaussian function. Actually,
Okay, let me have a look.
yeah.
And then the other part of the problem is like if I want to generate delay using photonic waveguide, I need to make sure that the size of the envelope does not get too huge because of dispersion, and because the amount of delay is quite large, and dispersion management is also one thing, and also nonlinear effect because this the amount of peak power goes out of the. I have never so physically
Hmm.
worked with such sources, but anyway. So
Okay.
is there, because I'm not sure whether it is
So how do you
still
introduce delay in your photonic circuit? Like what kind of elements do you use? Some kind
how
of
how
retarders?
I how I see is like if I have a, because for so femtosecond delays in, let's say, silicon nitride material would be only worth millimeter long waveguide spiral, so it would not be really unmanufacturable lengths. So variations of several microns to several millimeters, and that is
Okay.
easily fabricable at these MTW sources that we have. But I'm just not sure because because fabrication takes a lot of money, and before I
Okay.
need to little bit sure that if the nonlinear just breaks, if it burns the chip, it doesn't make sense. And
Mm,
also
yeah.
the dispersion changes the envelope, the size that also
Yeah, so
will
this
just.
dispersive element, you can model it in COMSOL. You can give that
Mhm.
particular element, whatever, give its material properties, and you can
Mhm.
see if it is dispersive or not. After you the
Yeah.
source, there would be a light source. You can nicely see its Gaussian, temporal Gaussian function, and then it goes through a one domain, and if there's a dispersion of it, so you can see that
Okay.
actually the
Okay.
delay and all those things you can see
Okay.
nicely. You can see in time domain simulation.
Okay.
Okay,
Let
this
me have a
example
look
that
at
I
it.
showed, it's a very good example to start with.
Sure, sure. Let me.
Sir,
And just a very small follow-up question: is that then because most of the time we take the material, but if we are working with a particular material and we don't have this this perfect refractive index
Yeah, so
model.
basically, you need to search some literature review and then use Origin Pro to extract this graph into XLS, and then you can XLS or any CSV format and then import. But yeah, if you don't have material properties, then yeah, it's very difficult. You have to search for a material property in the literature review if it is
Because
not
the
available in
manufacturer,
COMSOL. Yeah,
yeah, it is not a, and the manufacturer also are not very sure. So there is a
yeah.
combined option to do like a Selmayr equation study about it,
Oh, okay, okay,
but
yeah.
that will take really long time.
Yeah.
And until then, like just putting the refractive index without any extra values would just be like dart in the middle of nowhere. So
Yeah, that material property is always a challenge. Correct. Yeah.
okay,
So that's
let me
because
have a look.
console is just a tool.
Correct,
You
yeah,
will
that's what.
do whatever you want to do. So if you
Correct.
need to feed it with correct data.
Solving equations. Yeah.
Yeah. Correct. Yeah.
But yeah, okay. Let me see if I can find something. Okay.
Mm,
Anyway, thank you. Anyway.
okay. That's good. Thanks. Okay. Yeah. Hi, Sabita. You had a question?
just an addition to what Sir was discussing, maybe when a femtosecond laser pulses passes through the medium, there will be dispersion as well as nonlinear effects happen simultaneously, and then it will be very difficult to handle both the effects.
Okay. So I
Yes.
suddenly
So
lost
the
you.
the the source
Yeah.
manufacturer actually does have an option that once it comes out, it is a fiber coupled source, and
Um,
they can do this inverse dispersion, and they can do this all the magic and give you whatever that you need. So once that comes out of the source, then it is your job to then keep it in the same shape until you need it for your application. So
so,
right
what
now
is the
we are
repetition rate of that
100
femtosecond
megahertz.
laser megahertz?
100 megahertz, correct.
Ah, okay. Then peak hours may not be that high.
Hmm. Yeah, good point. Thanks.
Okay. Looks good. So that I hope that. So are there any more questions? I think we have more 2 minutes. Else we will wind up the session. Please.
Excuse me, sir.
Yeah.
So one small doubt.
Mm-hmm.
Actually, you already mentioned the meshing of user control mesh. So is it like you told about for plane surface? Will it be the same for a circular, let's say sphere? Also, meshing will be the same user control meshing.
So user control mesh we only use when we are doing time domain simulation, as I showed in the plasmonic whole array example that I've shared you. In that they use user control mesh. So in user control mesh only we need to use. In time domain simulation only we need to use user control mesh. Otherwise, we can use physics control mesh. Should not be a problem.
Yes, sir.
Whether it's any geometry doesn't matter. Frequency domain simulation you can do using this one. Okay.
Okay. Yeah. Okay, sir. Thank you.
Okay. So what we can do to end, we can means if you guys have a camera, you can switch on the camera. We can take a group snap screenshot of all the people together. It could be helpful to report. How about others? Are you guys available? Any other people? Yeah. Great. So yeah, looks good. So I will take few screenshots of these. Help me to put it. Hold on. Yep. Like you guys can smile like after this course, like like it's too much, I guess, for you guys. You successfully completed this hampering for 5 days. Yeah, that's good. Yeah. Okay, then hopefully this course was helpful for you guys for taking this forward your research. Okay, so good. That's great. You guys can reach out to me. I will try as my level best to get in touch with you guys if you have any questions. I will try my best. I cannot guarantee, but I will try my best. Okay, feels good.
Sir, I
Okay.
will
Sir,
meet you
if possible,
physically.
just look into that winter optics class.
Yeah. Definitely, yes. Definitely, will. I will try if we can. So we can share you the. Maybe we can put it in kind of a live kind of a session in YouTube, and we can take it forward. Yeah, that's a. Thank you for that suggestion. We'll definitely look into some. We can do a live broadcast and also record it. Yeah, it would be good. Yeah. Thanks a lot, Ayushi.
Thank you, sir. Thank you, everyone, for the input.
Thanks a lot,
All
everyone.
the best.
Take care.
Thank you.
Thank you, sir.
Thank you, sir.
Thanks a lot, sir.
Thank you very much.
Take care. Bye.